All right, guys, so we left off with our thermodynamics. So kind of as you can kind of see in second law of thermodynamics, that our work will begin to diminish sometimes whenever we go through and do a transformation. And depending on the system, and like we talked about, we have to make sure that we're choosing the best option of how do we get that efficiency? How do we get a diminished loss in the ability to do work? So for example, when we start to talk about like coal plants and things like that, factories, a lot of it's given off as heat. Just like in your nuclear power plants, just like in those, some of that heat is going out as hot water. And as that hot water, because they'll transfer it to that instead of out into the air, they'll go through and they'll transfer it into water, and that water goes into lakes nearby. And as that hot water goes there, it changes the dynamics of there. When water is hotter, it has less oxygen. And so if there's less dissolved oxygen, that means fish have less to breathe. If they have less to breathe, they don't do so well, kind of like you. You need to breathe, they need to breathe. All right? Then we go into the light bulb at the end. You're like, Miss, I thought those were better. You guys have been raised in the age of LED bulbs. Sorry, I got the hiccups. LED bulbs and incandescent bulbs are different. Incandescent bulbs will go through and give off a tremendous amount of heat. Those are those old school light bulbs, the cheap light bulbs, that when you touch them, they get really, really hot. But in the US, we're trying to, and they've been trying to phase those out completely to where we either have your lights that you have like in a classroom or a LED based bulb. And so as we switch, those you can typically touch and they're not as hot. LED's not hot at all. But our incandescent would be the kind where if you left your hand on it for any length of time, you would end up with a burn of some sort. Why? Because there's so much heat coming off of it. All right. So efficiency is something, like I said, one of the things that kills efficiency is heat. That's where most things are converted into, which then adjusts the quality, which then ends up with entropy. So entropy is whenever stuff starts to head towards disorder. So as you add heat to a system, what do you know that the molecules do? They're not nice and tight in a solid, or they're not nice and tight in a liquid. As we do, we start to cause those molecules, as you add heat, they vibrate faster and faster, and that's how we know, we talk about that. You add heat, you start to do phase change. That's that phase change graph that you learned in chemistry. So as that phase change starts to adjust, those little stair steps of peace, it gets to a certain spot, cool, we can handle here, but then the heat starts adding into it, and it starts to pull things more and more further apart. Means it's not as ordered. It's a system that goes towards chaos. So that's what ties into your second law of thermodynamics. Okay? So when we start to talk about systems, there's open systems and closed systems. Open systems means it can leave where it's at and go into another spot. Closed systems are within. So like your circulatory system, the part that moves your blood around, that's a closed system. And so you don't walk around like squishing out like a sponge. And so you are your circulatory system is a closed system. All right. So when we talk about input, output, that should be one's going in, one's going out. Use those standard stems to figure that one out. All right. And then steady is what we understand. It's something that's consistent. So going into your open systems is going to be like the picture of the earth on the left, the blue one. Okay. And so as you're looking at the blue, we have light coming in, but yet some light does go out where our atmosphere is not too thick, or the holes in the ozone, one of those two. Light can reflect out in some of those spots. Typically, our atmosphere shouldn't be super thick where it's like a blanket, but our CO2 emissions, methane emissions, things like that have made that blanket around us thicker, like we talked about in chapter 1. So less is being ejected and the efficiency changes for our system. Versus when we go into another aspect, that's energy. When we go to the green and we start talking about matter, that means, and remember, law of conservation of matter, matter can't be created nor destroyed. So whatever was on the earth because of our atmosphere. We don't fling it into outer space. We haven't started to launch our garbage. Haven't gone full-blown Wall-E yet either. So when we look at it, whatever was here is here. So it goes into the phrase, when you start to look at yourself, you are nothing but recycled materials. You are something that used to be something else. Goes with the phrase, you are what you eat. So the nachos you had yesterday, those are now part of who you are for some part of it. Some part of those nachos have left or will soon leave from yesterday. But other parts of those nachos are part of you. Some of those nachos have already been burned up and used as energy, especially for you little skinny kids, the ones that use and have a very high metabolism. Your body may have already taken those nachos, converted them to energy. You used them to go run and do and go and be and things like that. And it's already been released out of your body in the form of heat in some way. For some parts of it went to build other tissues and materials. So that's where you are that. Just like when an organism dies, it dies and becomes part of that soil. So that bug that was in the garden, that bacteria broke down, eventually went into the soil as one of those macromolecule sets, drawn back up by the plant and went into the next plant. And so, in essence, what that bug was is now in that plant. So we have that transfer of matter across. So same thing goes with the oxygen in our atmosphere. The oxygen you're breathing is probably the same oxygen that could have been in the lungs of Cleopatra, to Genghis Khan, to Dr. King. And so it's one of those things that there's no way to get rid of it, not unless, like I said, we sling it into outer space. Everything that was is still here from the inception of Earth. It just got converted into something else. All right, so that's where we need to understand how those things are recycled. All right, so when we talk about something that's steady state, that means what goes in and comes out are equal. There's no change. It's very ordered. Stuff is consistent. So those of you who have kind of, in that picture has like the bucket with the leaks or amount of what's in versus out. But we have that with a lot of things. So if there's no change, means our inputs and our outputs are equal. So kind of like they talk about in dieting. If what you eat equals the amount of calories burned, your weight shouldn't change. If you decrease your calories and keep up the same activity, your weight will go down. If you increase your calories and decrease your activity, your weight will go up. It's that input-output system. So it kind of ties that way. So then we have two ways that can happen. We can either have a negative feedback or a positive feedback. So as we go through and we start to look at our diagram, positive one is one that's just an ever-increasing and ever-spiraling situation. So in this particular case, when we talk about population increase, well, if I have new people will eventually hit puberty, and those people that hit puberty will eventually get old enough to have babies when they're married, and whenever they have those babies when they're married, population increases. Guess what? The babies they just had, guess what's going to happen? They're eventually going to grow up and have more babies. And so that's why we see that human population spiraling up and up and up and up and up. As we talked about, could be in as little as 20 years, we could already be at 10 billion people. Positive feedback loop. And remember that population stuff was what we talked about in chapter 1. So then when we start to talk about a negative feedback loop, that means it's basically, that one's like a ping pong match. It's like that one pops it, the other one pops it back. That one pops it, that one pops it back. And so it's a constantly back, forth, back, forth. So you go through, you're working out. What do you start to do? You start to sweat. What is the purpose of the sweat? Is to cool you off. So then you're not as hot anymore. So you keep working out, you keep getting hot, you keep sweating, you cool off, you go, and it does that toggle back and forth. Same thing. You eat breakfast. You gave yourself energy. Cool. Your body burned through the energy. Used it up. Your body gets the signal. Oh, your stomach going, arrgh. Tells you, oh, I'm hungry. You go eat. Your body has energy, doesn't want it. All of a sudden, then energy starts running low. You get, hungry. Stomach growls. You go, oh, I need to eat. And it's just that back and forth. That's your negative feedback loop. And that's all we have for chapter 2.